Hi everyone. We will be starting on this week's material. We are going to be working from Chapter 10. And the topics today are mostly going to be intermolecular forces and some different diagrams on temperature and pressure. And so it's a lot of basically concepts that I'm going to be answering for this kind of material. So let's jump right into it. Awesome. And also let me know if you can hear me okay, and if my screen is visible for you as well, and if nothing's like frozen. That's always a good thing to let me know. I will keep an eye on it as well. Okay, so let's jump right into it. Chapter 10, like I was saying. Yes, and we are going to be working on question number 5. So this question asks, what is the evidence that all neutral atoms and molecules exert attractive forces on each other? So the reason why we know that this exerts positive attractive forces on molecules and even neutral atoms is because of van der Waals forces, first of all. And that's why neutral atoms can have this attractive force because of van der Waals force, because of that temporary attraction that, electrons and the nucleus can have momentarily with things. And the reason why we know this is true is because that we would not have liquids or solids or gases, regardless of temperature, if we did not have van der Waals forces into play. So that's why we know that this is true. So we would have no liquids, solids, or gases, regardless of temperature. Okay, so let's move on to the next problem. It says define the following and give an example of each. So the first one is the dispersion force. And the dispersion force is the attraction force in the van der Waals effect that temporarily happens when atoms are in constant motion, and then it'll have a temporary attraction between the two atoms or molecules or what have you. So that is the attraction force. And it is temporary and from constant motion of atoms / molecules. So that is 7a. And so for 7b, dipole-dipole attraction is similar in the sense that it is kind of like dispersion force, but it then manipulates the actual molecules to rearrange themselves to then attract, oppositely charged things close in contact. So let me write that down. This occurs when the atoms in a molecule shift electrons when in contact with another, I'm going to just say particle. So that can be an atom or a molecule or something like that. So dipole-dipole attraction is really important. It happens a lot. So it's a very strong force because of that kind of shift in electrons, and therefore you'll have like more stronger bonds than the dispersion force, because the dispersion force is very temporary. It happens just maybe for a second, or maybe not a second, but it happens very, very quickly. And so for hydrogen bonding is similar to the dipole-dipole attraction, but it is when hydrogen is attracted to electronegative atom, which is, oxygen or I believe fluorine, but it's the hydrogen is bonded, or not bonded. It is highly attracted to the highly electronegative atoms, and then it creates a partial charge because of that shift. So this occurs when hydrogen is attracted to high electronegative atoms and causes a partial charge. Concentrated, I should add, charge. And so that is what hydrogen bonding is. So now that we know those kind of base factors, let's move on to 8. 8 is the question of the types of intermolecular forces in a substance are identical, whether it is a solid, a liquid, or a gas. Why then does a substance change phase from a gas to a liquid to a solid? The answer is pretty simple, actually. So it has to do with the intermolecular forces and then the thermal energy. And so there's three different things or three different balances between those two that will cause a solid, a liquid, and a gas. So when thermal energy, I'm just going to abbreviate it, when thermal energy is much lower than the intermolecular forces, then that is going to produce a solid. When the thermal energy is a little bit less or equal to the intermolecular forces, so like a little less or equal here, than the intermolecular forces. And the intermolecular forces are the dispersion, the hydrogen bonding, or dipole-dipole, those are what's going on. If it's a little bit less or equal to, then that will be a liquid. And you might be able to assume here, if the thermal energy is a lot higher than the intermolecular forces, then it creates a gas. So these are the three different ranges that will have a substance change phase in the first place. So now let's work with an example. I can leave this up if you're still working on it. But the next one asks, neon and HF have approximately the same molecular masses. A, explain why the boiling points of neon and HF differ. And B, compare the change in the boiling points neon, argon, krypton, and xenon, I believe that's how you say it, with the change of the boiling points HF, HCl, HBr, and HI, and explain the difference between the changes with increasing atomic or molecular mass. That is a lot to take in, but here's it all written out. So we're going to work on 10A for the first part. And I just went ahead of time and just put in all of the boiling points and the molecular masses for everything, so that we don't have to look that up. But for 10A, neon and HF. So neon is a noble gas. Noble gas. And HF has hydrogen bonding. And because the noble gas, neon, it has dispersion forces. It's just neon, it's just one atom. It's already a gas, it doesn't have anything bonded to it. So it's going to just have dispersion forces. And the HF, it has hydrogen bonding. So that is going to have a much stronger bond, which makes it more difficult to change state. So it needs more energy. It needs to have more energy to be required to boil it, to move it up a phase. So that is why the boiling points of neon and HF differ. And right here, this is neon. Hopefully you see that in pink right there and there. Neon, it's a much, much lower temperature that it needs to boil. So it doesn't really need to take that much at all. It's very, very cold, negative 248.7 degrees Celsius. And for HF, it needs to be 19.5 degrees Celsius for it to boil. So the HF needs a higher temperature, more energy, because it has hydrogen bonding. It takes more energy, in conclusion. So now let's move on to 10B. I already touched on the neon and the HF, but let's go through all of these. So with these two boxes here, these are the boiling points, and then here's the molecular masses. As you can see, possibly, let me zoom in here so you can see better. For this one right here and this one right here, they have pretty similar molecular masses. Same with the 39, the 36, 85, 80, 130, 128. So these are all pretty similar on their molar masses, but their boiling points are a lot different. As you can see, we were just talking about neon and HF, negative 248 versus positive 19.5. That's a big difference. And so the reason why it's so much different is because HF, of the boiling points on the right with all these hydrogens, hydrogen H or the HF, the HCl, HBr, HI, these have higher bonding than the other noble gases because of they're not dispersion forces. The dispersion forces on the left are only what is really happening with the noble gases. But when you look at the neon gas or the noble gases, when it increases in molecular weight, it has a higher boiling point because when it weighs more, there is a connection with higher molar mass, higher boiling point. That has to do with it takes more energy to boil all those different different electrons and whatever is in it. It takes more because it's larger. So whatever it's made out of, if it's bigger, it's going to take more energy to do so. So there's a correlation with both categories on the left and right. You can see that happening. So higher molar mass, higher boiling point, and because there are dispersion forces on the left, it's going to have lower boiling points because it takes less energy. And when we look at specifically these right here, all the hydrogen ones, there's a correlation with not only the hydrogen bonding, but also the forces between each other. So the HI is actually the highest because it has a higher molecular weight, and because of that, it's going to have the highest of them, because these three right here is not hydrogen bonding, but they do have dipole effects. HF is hydrogen bonding, so HF is going to be the first because of the hydrogen bonding. So I'll say high bond. But number 2 is going to be HI, and then it's going to be HBr and then HCl because of the molecular weight. Because the hydrogen iodine here, it weighs the most, and then it follows these two being more light because of that molecular mass difference. Then it's going to decrease in boiling point, just as the same effect with the noble gases. There's higher molar mass, higher boiling point, but the HF, even though it weighs the least because of the hydrogen bonding, it's going to have the highest boiling point. So let me just finish my note right here. And then for 2, then it's HI, and then HBr, and then HCl. So that is the order for those. Okay, now let's move on to question 24. So question 24 says the surface tension and viscosity values for diethyl ether, acetone, ethanol, and ethylene glycol are shown here. A. Explain their differences in viscosity in terms of the size and shape of molecules and their IMFs. And B. Explain their differences in surface tension in terms of the size and shape of their molecules and their IMFs. So this one is very similar to the problem 8. And we can see that with the periodic table, the trend is that as you go down the periodic table, the polarity goes up. So that is a trend that is happening. So I'm going to write that down. As polarity goes up as you go the periodic table. And not only that, as in when there's a higher polarity, then there's going to be more of the hydrogen bonding. And when there is more HB, hydrogen bonding, then there is going to be a higher surface tension and viscosity. And so you can see this as we go down. This is going down the periodic table here. Let me correct what I'm saying. As you go down the periodic table, you're increasing in polarity. This is already going down in the periodic table, these different compounds here. So we can see that the surface tension is 17 and it goes to 48, so it's increasing. The viscosity is also increasing. And not to mention the diethyl ether, it's least polar, and this is the most polar. And of the ethanol and the ethylene glycol, there is two, I'll write that down, there's only one OH group here, and there's two OH groups here. And so because of that factor, it increases the surface tension and the viscosity because there's more of that bonding, so it's going to have higher surface tension and viscosity. So let's move on to 27. 27 asks or says the surface tension and viscosity of water at several different temperatures are given in this table. B or A, as temperature increases, what happens to the surface tension of water? Explain why this occurs in terms of molecular interactions and the effect of changing temperature. B, as temperature increases, what happens to the viscosity of water? Explain why this occurs in terms of molecular interactions and the effect of changing temperature. So it is very similar to what we were talking about before, as in those three different ranges. So the three different ranges I was talking about was the thermal energy, and if that is less than IMF, solid, and then if it's less than or equal to IMF, then it's a liquid, and if thermal energy is more than IMF, so the intermolecular forces, it is a gas. So these are the three different ranges, and so when the surface tension and the viscosity goes down, the thermal energy will go up. So on that basis here, if we look at this table, the temperature of the water is going up, so thermal energy is going up. And so because the thermal energy is going up, the surface tension and the viscosity is going to get lower because it's going from 75.6 to 58.9. The viscosity is going from 1.79 to 0.28. So all of those are going down in the values as the temperature goes up, and that is the thermal energy basis. So this goes along with those three different ranges I was talking about, and so because of it, there will be less of the intermolecular forces happening. So that is the changing effects of what is happening when you boil that water. So now let's move on to question 54. From the phase diagram for water, determine the state of water at 35 degrees Celsius. Let me actually just zoom out all the way. There we go. Actually, let's go back. Sorry about that. I just want you to see it properly. Okay, so let's look at this. For question A, 35 degrees Celsius and 85 kilopascals. So from this diagram here, if we try to find, you might not be able to see it very well. Let me just zoom in. Hopefully that's a little bit better. So at 35 degrees Celsius, it would be around this point right here. Right here. This is 0.1 or 0.01, and this is 100. So it's just a third in between those two. And then at 85 kilopascals, it would be somewhere along here, maybe right below the 101 part. So for this, it would be at a water phase, matching those two up. So this would be at water. And so now let's look at negative 15 degrees Celsius and 40 kilopascals. So negative 15 degrees Celsius is going to be around, it's a little bit of a guessing game with this graph. I wish it was a little bit clearer that they provided, but we'll do our best. Negative 15 could be maybe around here. And 40 degrees or 40 kilopascals is somewhere right here. So as you can see, it's in the blue, and this is going to be ice. Now let's move on to C. We have a temperature of negative 15 degrees Celsius as well, and 0.1 kilopascal. So when we go back to the negative 15, and then 0.1, so I'm thinking it might be, I don't know if this is, it looks like these values on the left, it's not linear, I mean, because this is 101 and this is 22,000, so I'm thinking 0.1 is maybe somewhere around here. I said it was ice, possibly, but it's not as clear as maybe other graphs will be when maybe you take a test or a quiz, hopefully. So I'm going to say, it's actually closer to the bottom here. I'm going to say it's a gas because it looks like it could be in the brown area instead. So I'm going to call it a gas. Okay, so now let's move on to 75 degrees Celsius and 3 kilopascals. 75 could be like right here. 3 kilopascals is somewhere right here. It's going to be a gas for sure. And the last two, 40 degrees Celsius and 0.1 kilopascal. So that could be possibly right there. And then 0.1, it's going to be a gas as well. And the last one, 60 degrees Celsius and 50 kilopascal. So maybe like right there, and then 50, which is actually harder to tell because it looks like it's on that line. So if it's 50 here for sure, halfway that point, and then 60 could be like right there. I'm going to call it a water because it looks like it is more in the purple region. So that's how you kind of find those different phases from the graph. So now let's move on to question 56. Okay, so question 56 actually has a little bit of calculations. And it reads, pressure cookers allow food to cook faster because of the higher pressure inside the pressure cooker increases the boiling temperature of water. A particular pressure cooker has a safety valve that is set to vent steam if the pressure exceeds 3.4 atmospheres. What is the approximate maximum temperature that can be reached inside this pressure cooker? Explain your reasoning. Okay, so for this problem, we are going to be using the equation natural log of P2 and P1. Those are the pressure values. And the change in vapor enthalpy divided by the R constant times the inverse of temperatures 1 and 2. So this is the equation that we're working with here, that we can plug in some values and see what the temperature 2, the maximum temperature, it can be reached at, P2 3.4 atmospheres. So let's just think about what all of these variables will be representative. So we just said P2 is going to be 3.4 atmospheres, and P1 is going to be at 1 atmospheres, because at 1 atmosphere it can be, the temperature is going to be at 100 degrees Celsius. So T1 is going to be at 100 degrees Celsius when it starts to boil, but since we have to work with Kelvin, we need to add 0.27315, 0.15, and then T2 is going to be unknown. The R value is going to be 8.314 joules per kmol. And then the vapor value here, let's just move this over here, is going to be 39.67. And that is in units of kilojoules per mole. Okay, so these are all the values that we're plugging in. So P1 and T1, 1 atmosphere, 100 degrees Celsius. And then P2, it's going to be at 3.4 atmospheres, and so there's an unknown final temperature. And so let's do some algebra to isolate T2 here. So I'm going to, what I like to do when I have a huge equation that I have to solve for like one variable, what I tend to do is I do it in my head, which is not always the best thing to do, but if it works for you, it works for you. But I will talk through what I'm going to do instead of writing it all out, because it can get messy. So to get T2 here, I first have to multiply by R on that side. And so we'll have an R natural log P2 divided by P1. And so now that we've got the R out of the way, we need to divide by the vapor, H. And now we're going to be left with this. And so to get rid of that, we need to minus a T1. A T1. And then once we minus a T1, what will be left is the negative 1 over T2. So we're going to multiply everything by negative 1, and then also put the inverse of it, because 1 over T2, that's 1 over T2. So if you flip it, all you have to do is put it to the power of negative 1. So that's how we can isolate it for that variable. And so now we can just plug everything in. And when we plug in all those values that we found on the left here, it will give us a value of 412.6 Kelvin. Or if we subtract 273.15 from Celsius to Kelvin, it is also 139 degrees Celsius. So that is the answer for the final maximum temperature that this pressure cooker can be at that pressure that it gave us. So let me write that down, because the question asked to explain my reasoning. So using the formula, we have found the max temperature when the pressure cooker is at 3.4 atmospheres. Okay, so that's the answer for this problem. Moving on to the next problem. I believe this is almost, so we have 2 more problems left. 58. So this one asks to determine the phase changes that carbon dioxide undergoes as pressure is increased at a constant temperature of A, negative 50 degrees Celsius, and B, 50 degrees Celsius. That's positive 50 degrees Celsius. And if the temperature is held at negative 40 degrees Celsius and also at 20 degrees Celsius. So I'm going to write, so at negative 50 degrees Celsius, at positive 50 degrees Celsius, at negative 40 degrees Celsius, and at negative 20 degrees Celsius. So these are all the temperatures that we're going to be looking for. Okay, so if it is held constant at this temperature, let's do the first one, negative 50. So if it is held constant at negative 50, it'll be going from a gas to a liquid and back to a solid. So that is the phase changes that will happen. So gas to a liquid to a solid. And so at positive 50, at positive 50 degrees, it'll go from a gas to SCF. And at negative 40 degrees Celsius, that might be, this is like negative 25, that's at like 36-ish. I'm going to say it's like right here. It's going to be the same as the, at negative 50, it'll go through the same the phase changes as gas to liquid to solid. And so just to be clear here, I'm going from like this all the way up here as it's increasing in pressure, going from gas, liquid, and then this is the solid region right there. And so the final one at negative 20 degrees Celsius. So that could be maybe like right, this is 25, so I'm going to say right here. It's also going to be going from gas to liquid to solid. And so those are all of the phase changes for increasing the pressure for CO2. Now let's work on the last problem for the day. This one says, it's 62, is it possible to liquefy nitrogen at room temperature? About 25 degrees Celsius, that's what room temperature is. And then I wrote the conversion to Kelvin here, which is also 298. Is it possible to liquefy sulfur dioxide at room temperature? Explain your answers. So the one on the left is going to be, actually let me just look at my notes here real quick. The one on the right is sulfur dioxide, and the one on the left is nitrogen. So these are the two phase diagrams. So as we can see here, this is 25 degrees C right at this point. It will never be able to be liquefied because even though we're increasing in pressure right here, at this 25-degree line, it goes from a gas to a supercritical state. So it is not able to reach the liquid stage, even if you increase the pressure to exceeding values. So no, nitrogen cannot liquefy at room temp. But let's look at the sulfur dioxide phase diagram. So the one on the right here, like I was saying, 25 degrees Celsius is the equivalent of around 300 Kelvin. So that is the line right here. And so as we can see, actually, there is a liquid region right here. And so if we increase the pressure, this is a 0 mark right here, so that's 0. This is 0, and this is around at 6 log of pressure, so log bar, that's just a unit of pressure. So that region of pressure, 0 to 6, it can liquefy. Yeah, that's the full sentence. At sulfur dioxide pressure, 0 to 6, it can liquefy. So that is the region that you would need to change it to. Because we're holding temperature constant, the only thing we really can do is just increase the pressure, and that's why we can change those states. So that is actually it for today. I don't have as much as the weeks prior because a lot of these are just concepts. Let me know if you have any questions, and as always, this will be posted to the PSU Learning Center's YouTube channel, so you can always rewatch any of the recordings there. But if not, good luck on your tests and any of your future assignments, and I will see you all next week.